So when you get these problems, a really good practice to do is go through and then immediately write down what each of the pieces of information are that they gave you so that you can try and figure out what kind of problem is this? Because until we know what they gave us, we don't necessarily know what options we have for what kind of problem it is. So this one, kind of similar. We did an energy drink one. This one's going to be like very similar type of problem, but different numbers. A soda company claims that its cans contain 355 milliliters of soda on average. Okay. This is a claim from the company. The claim generally is giving us that number that we're going to be using as the mu naught for the null hypothesis. So they just said the company is claiming the cans of soda have 355 milliliters in it. So that's going to be an average or a mean. And we usually denote it as the mu naught when it's the claim. So I'm going to write 355 is our mu naught here. A quality control inspector suspects the actual volume is less. So the quality control person saying, I don't think they're actually giving you 355 milliliters of soda in most of the cans here. She tests 36 cans. So we just got an N. That's a sample. Okay. And finds that the sample mean is 353.5 milliliters. So we got a sample mean. That means we got an X bar. The population standard deviation is known to be 5 milliliters. So we got a sigma. Is there enough evidence at the 0.05 or the 5% significance level to conclude that the mean volume is less than 355 milliliters? So they just gave us the alpha. The alpha is 0.05. All right. So when we're trying to figure out what type of test this is, aside from the fact that at the top I have z-test written there, the thing that would have let us know, like if you were taking an exam, is I'm looking through our info here and we have the sigma. We got the population standard deviation. So going back to that chart that she gave you, our question at the very, very top is sigma known? And the answer is yes. So we're going this way. So we're going to end up in the land of the z-tests. Okay. So we already knew that based on the title of this paper, but if it were an exam, that would have been the first thing we would have asked ourselves. Did we get the population standard deviation? Yeah, cool. So this is going to be a z-table problem. If the answer is no, we're probably going to be on a t distribution, but we'll worry about that later. Okay. So when we're doing a hypothesis test, we need a null hypothesis and we need an alternative hypothesis. The null hypothesis is always the boring one. It's the thing that would mean status quo, business as usual. Business as usual is usually what the claim is telling you. Not always, but it's often what the claim is telling us. And here it's saying the claim is that the can of soda has 355 milliliters of soda in it. In this case, that would be the boring news. It would mean the company's not lying to you. So we're going to write our null hypothesis then. And so we're going to say H naught. That's the way we write a null hypothesis. The other hypothesis, we put an A after it. That's the alternative hypothesis. And how we write the null and the alternative hypothesis is going to need us to remember that the null hypothesis always has to have the equal sign in it somewhere. It could just straight up be an equal sign. It could be a greater than or equal to sign. It could be a less than or equal to sign. The alternative hypothesis is either going to be a not equal to sign, or it'll be a greater than or a less than. It doesn't have the equal to sign in it ever. So how we figure out what the null hypothesis needs to be, in this case, actually really depends on the alternative hypothesis. And that we're going to get when we come down here and we say, a quality control inspector suggests the actual volume is less than the 355. So I'm going to write that the alternative hypothesis is that the mu naught is less than 355. Why am I writing that one down first? Well, because when she's saying she's concluding that she believes the volume is less, then that means that up here for your null hypothesis, what's the opposite of that sign? What's the opposite of a less than sign? Yeah, so I'm going to turn that sign around and put the equal to sign on it like that. It would have been okay to say it was just equal to. It just feels a little bit weird when you're like, well, the opposite of equal is less than. It doesn't feel like it. But if you just wrote that, because the way it says it, a soda company claims its cans have 355 milliliters of soda, you could say mu naught is equal to 355, but you don't get to put not equal to down here because of what the quality control inspector said. The quality control inspector only believes the volume is less. She doesn't believe that it's less than or maybe more than. She believes it's only less. So the alternative hypothesis has to be this one. Usually you could just write the equal sign there or greater than or equal to. For me, it just makes more sense to write greater than or equal to because that's the opposite of what the less than sign is. Question?
So would the claim then be the alternative hypothesis?
The claim in this case, no, the claim is this one. Because it literally says a soda company claims its can contains 355. So it can't be the alternative because it's claiming the opposite of the alternative hypothesis. It can't be that.
Is it like allowed to be the alternative?
Yes, it is. Sometimes it is. And so that's where when people, sometimes as a multiple choice question, they'll say the claim is always the same as the null hypothesis, or the claim is always the same as the alternative hypothesis. Nope, it can switch. So you actually have to read the problem carefully. In this case, they told us the claim is actually that it contains exactly 355 milliliters here. So the claim is actually not even the null hypothesis the way that I wrote it, but we could have written the null hypothesis was just an equal to, and we'd still be okay there. That wouldn't be a problem. Null hypothesis has to contain the equal to. Alternative hypothesis is going to be whatever it is that we're testing. We're testing, is it possible they're lying to us and that there's actually less than 355 milliliters in there? That would be interesting, right? It wouldn't be interesting to find out they're telling us the truth. Oh, there is 355 milliliters in there. Okay. That wouldn't make a story for you to write. That wouldn't make a thing that you'd want to go tell people about. So our setup with the hypothesis here is going to tell us, is this a one-tail test or a two-tail test? What are we testing? Testing that one. So since we're testing, is the volume actually less? We're only testing in one direction. So this is a one-tail test. This pen is shot. Poor dead pen. Okay. So we have a one-tail test. That'll be important later, not quite yet. Okay. Now what we need to do is look at her formula sheet for the type of test that we're using. So we're looking for population mean. So it's either this one or this one. But in this case, our sigma is known. So we are using our Z test statistic. So I'm going to write down that formula for us. Our Z test statistic is X bar minus the mu naught divided by our sigma over the square root of our sample size n. Right, we're plugging stuff in now. When we plug stuff in, what we're gonna get is a z. And we're gonna use that z table to go find a p-value. So that's always sort of the progression here. We're gonna go find the test statistic z and use the table to figure out what the p-value is. So X bar is 353.5. My mu naught is the 355. My sigma is just 5. And we're dividing by the square root of 36. So I got negative 1.8 when I did that. So I'm going to draw myself a little picture now. Of my distribution. Okay. Negative 1.8. So remember, 0 would be right down the middle. So negative 1.8 is over here. So I'll put like a bar maybe right here at negative 1.8. And the question is asking about whether or not the volume is actually less than this amount. So we're talking about this part of the graph. So when I go find the p-value for z is negative 1.8, the way that the z table works, it always gives you the area from here up to whatever the bar is. Since that's actually exactly what I want, I don't have to do any 1 minus or anything crazy. Literally, the number that I get out is going to be the p-value that I need. So we're going to go get our p-value. So we're using that z, negative 1.8, to go get our p-value. So on my table, negative 1.8, 0 would be that very first column there. So 0.0359 is my p-value. And that's exactly the number that we're going to use. We're not going to do 1 minus anything because of the way the z table works. The z table always goes from the left-hand side up to the z-score. And since our z-score is right there, that's exactly the area that I also said I wanted. So we're good. All right. How am I testing this at the 5% significance level? What does that mean? Okay, so she had you take notes. She had you look at significance levels, and she needed you to go find p-values. At this point, you're doing something with that p-value, and you're doing something with that significance level. What are you doing with those two numbers? So this number here and this number here are the two important numbers right now. What am I concluding? You're looking scared. You're comparing those two numbers at this point, and what am I hoping for? I'll say it differently. I'm a dork, and I want to say something interesting happened. If I want to say something interesting happened, I want to get to reject the null hypothesis because the null hypothesis is boring. I want to get to say something interesting. I only get to say something interesting if my p-value is smaller than my alpha. I only get to say something interesting if my p-value is smaller than my alpha. I only get to say something interesting if my p-value is smaller than my alpha. So look at that p-value and look at that alpha. Am I happy? Yes. My p-value is smaller than my alpha. So I get to reject the null hypothesis. I'm excited. I get to say something interesting now. Okay. So I'm going to write down because our p-value (0.0359) is smaller than our alpha, which is 0.05, we reject the null hypothesis. So I got to say something interesting. Okay. If I reject the null hypothesis, then if I needed to like write a conclusion here on what actually happened, I'll come over here because I need a little more space. There is sufficient evidence to conclude that the true mean volume is less than 355 milliliters. Is what our alternative hypothesis said. So the alternative hypothesis said that the true mean volume is less than 355. So because I got to reject the null hypothesis, that means there's sufficient evidence to conclude that this is the case. There's sufficient evidence to conclude that the true mean volume is less than 355 milliliters. Yes.
I have a question. How can you tell again that it's one tail or two tail?
So when it says something like a quality control inspector suspects the actual volume is less, she's not saying, or it could be more. She's saying it could only be less. So that's one direction. So that's one tail. If instead this said a quality control inspector suspects the actual volume is different than 355, if she's just saying different than, it could be higher or it could be lower. That would make it a two-tail test. But if she actually specifically says, I think it's more, or I think it's less, then it's a one-tail test. Yeah.
Gotcha. Thank you.
And I do have an example of one on the other side of the paper that'll be a two-tail test. We're just starting with some one-tails. Okay. So key takeaways here. When we go through, we need to figure out what kind of test we're doing. For this paper, all of them are z-tests, so there's not a whole lot for us to know. But when you're actually doing your exam and you have to be able to figure out for yourself what kind of test it was, our hint was that we got the sigma. Because we got the sigma, we're doing a z-test. Okay. Second thing we needed to do was use the information given to figure out our test statistic. When it's a z-test, the test statistic is a z. And so we got negative 1.8. You use that z to go get your p. Because ultimately, when you're doing a hypothesis test, you're always going to be comparing the p-value to your alpha value. The thing we're hoping for, if we want to say something interesting, is that your p-value is smaller than your alpha. We always want the p-value to be smaller than the alpha for us to get to say something interesting. If the p-value is bigger than the alpha, we don't get to say anything interesting. We just say, we failed to reject the null hypothesis. We don't have sufficient is the word I want, sufficient evidence to conclude whatever our alternative hypothesis statement was. Okay. So we're gonna do this all again with another example. I promise it gets more clear as you go, because you'll be like, oh, okay. We're just doing the same thing over and over again. We are. But the words change, and so certain things and details we got to pay attention to. A national study reports that college students sleep an average of 7 hours per night during the semester. Okay. This is what the study on a national scale is saying. This is not anything that a researcher has done yet. So in this case, our mu naught is serving as our claim that college students sleep 7 hours a night during the semester. Okay. A campus wellness coordinator thinks that students at their university sleep more than the national average. Okay. He doesn't say, I think they could be sleeping less or they could be sleeping more. He specifically says, I think they're sleeping more. So in terms of what it is that our alternative hypothesis is going to be again, we're going to have a one-tail test because he's saying, I think they sleep more. So if I come down here to do my H naught and my HA, he's saying that the average amount of sleep is more than 7 hours. That's the alternative hypothesis. So we could write up here that the mean amount of time is equal to 7. That would be okay, but that feels a little weird because it's not really the opposite of that. So I would say less than or equal to 7, but you could put equal to, it wouldn't be wrong. It just has to include the equal sign. So either an equal sign there or a less than or equal to sign there. But we don't have a choice on the alternative hypothesis. That one has to be greater than. Because it's just a greater than, this is a one-tail test. Which again, doesn't matter just yet, but it'll matter when we do the picture part. So I'm going to keep reading. He surveys 49 students. Okay, we got an N there. Okay. And he found that their mean amount of sleep each night was 7.3 hours. So that's a sample mean for just those 49 students. So we got an X bar now is 7.3. The population standard deviation, so that's a sigma, is known to be 1.2 hours. Because we just got a sigma, I'm like, a z-test, but we already knew that based on the paper, but that's okay. If we didn't, there's where we found out it's a z-test. All right, now, do the data provide sufficient evidence at the 0.01 significance level that students at this university sleep more than the national average? So we just got our alpha there. The alpha is 0.01, or a 1% significance level is another way we could say that. So I would always start these problems by writing out all the stuff you got. Now that this is what we have, we're gonna go find our Z, our test statistic. Our test statistic is gonna be the X bar minus the mu naught divided by the sigma over the square root of your sample size n. So you're just gonna plug in everything they gave you. I should get a positive z-score because of that numerator up there. I got 1.75. So it's gonna let me draw a picture now. Okay. So zero's right down the middle, so 1.75 is gonna be like over here. So I'll put 1.75 down like right about here. Okay. And here's something that we have to keep in mind. The Z table is going to give me this area all the way up to that number. So I'm going to shade that part in with blue. This is what the table is giving me. It's giving me this whole area all the way up to that Z value of 1.75. What that would give me if I put that number down is the probability of all the people up to that point. So that's all the people sleeping up to that amount of time. But the campus wellness coordinator thinks that their students are sleeping more than that amount of time. So they actually want that part. So I'm going to shade that part red. So I want the more than the Z value part of this graph. But when you go look on the table gives you the blue part. The table always gives you from the left all the way up to the number. So we're going to get the opposite of the number that I want. So what do I have to do with the number when I get it? Subtract from 1. So to actually get the number that I want, we're going to go look at the Z table for 1.75. That's going to give us this area, but I actually want this area. So when you get that number, you're going to do 1 minus whatever number we find.
So we kind of been doing that, right? Every time it says like more than, we always subtract them as we just continue.
You just continue doing that. So when we were talking about the Z stuff before, that part didn't disappear. We were learning all that because that's ultimately everything you've been doing so far this quarter is leading up to hypothesis testing. Because really, when you're doing research, what you're doing is hypothesis testing. So we were just learning all the basics. Now we're actually applying it.
Is 1.75 the same deviations?
Yes,
Okay.
above the mean. So that Z-score is still what Z-scores meant before. It's how many standard deviations above the mean. And our mean, whenever we're talking about a standardized graph like this, the mean's always at 0. So we're putting the 1.75 over here. Okay. Sorry, I cut you off.
No, it's what she said. I was just reconfirming every time it says like that they want more versus subtract.
You're gonna subtract from 1.
From 1.
Yeah, I know. You're like, that's what I meant, Jen. Like, yeah, don't subtract 1. From 1, yeah, subtract from 1. So I'm gonna go get our number 1.75. So we're on the positive Z table. The 1.75 is gonna be 0.9599. So the p-value that I got is this blue part. But to get the p-value that we actually want, we're going to do 1 minus 0.9599. And we get 0.0401. So another way we could talk about these when we say a one-tail test, we could say right tail versus left tail. So the area of the right tail is the p-value for the right tail. So this area right here is that p-value right there, right tail.
So whether it's a left or a right tail changes the how you solve for it.
Right. So this one up here was a left tail test. So I could write that up there, left tail. And then this one is a right tail. So left tail test, just take the number. Right tail test, 1 minus the number. Yeah. Okay, but now what we're doing with the p-value and the alpha is exactly the same as what we did last time. So we're looking at our p-value, 0.0401, and you're looking at your alpha, 0.01. In order to say something interesting, we want the p-value to be smaller than the alpha. Boom. My alpha is smaller than my p-value. My p-value is bigger than my alpha. So because this happened, we have to fail to reject the null hypothesis. So I'm going to say because our p-value 0.0401 is bigger than our alpha, we fail to reject the null hypothesis. So last time we started our conclusion with there is sufficient evidence to conclude. This time we're going to say there's not sufficient evidence to conclude. Okay, there's not sufficient evidence to conclude that, and now we have to figure out how to finish this. What we were trying to say is that students slept more than 7 hours per night. There's not sufficient evidence to conclude that students sleep more than 7 hours per night. So we found all of our info. Use that to go get the z-score. The z, you should always draw yourself a picture to try and figure out what part of the graph is shaded and what part you want. In this case, we were getting all of this from the table, but what we actually wanted was the other tail. We wanted the more than part. So that's why we had to do the 1 minus what value we got from the z table. So that popped out the p-value for the right tail. Always, what you're doing at this step is comparing that p-value to the alpha. And in order to get to say something interesting, the p-value has to be smaller than the alpha, but our p-value was bigger this time. So we didn't get to say anything interesting. So that's why we failed to reject the null hypothesis.
I don't know if you like know this or not, but do you know if we'll have like this reference on the formula sheet for the exam, or is this something we have to try and memorize?
So I don't remember her giving them that chart for the exam. So I think you have to memorize, but what you're really memorizing is you got the sigma Z. You didn't get the sigma T. There's more stuff on that table that helped with a lot of the homework questions as well. But when you're talking about the hypothesis testing, really it all comes down to, did she give you the sigma? If so, then it's got to be on the Z, because that's really our only direction we're going. Or did she not give you the sigma? Then it's going to have to be a T.
For discussion, if you do it from the modules and then go to discussion, she has it posted.
So under modules, go to discussion week 8.
Yeah,
She's already posted your formula sheet.
yeah, where you like reply to it, like above it.
Okay, good hint. Thank you for being the sleuth for the class. Okay. All right. I got one more for us. A manufacturer claims that its LED light bulbs last 10,000 hours on average. Like literally when you go into Home Depot, like they have those claims on the sides of the box. You're like, 10,000 hours. Oh my gosh. A consumer watchdog group tests a sample to see if the bulbs last a different amount of time than advertised. So this time they've listed stuff out for us. That's nice. Population standard deviation. Ooh. The fact that we got the population standard deviation tells me we're on a Z test. So using the same rule. Sample size is 64. So they tested 64 light bulbs. Okay. Sample mean was 9,850 hours. So that's not quite 10,000. It's seeming like maybe they're lying to us about our light bulbs lasting 10,000 hours. It's seeming like they might be lasting less. But this could just be we were unlucky with the 64 light bulbs that we picked. Maybe if we picked a different 64 light bulbs, we would have gotten a different result. So that's why they do hypothesis testing. So hypothesis testing, you come up with like a, it's feeling like that number isn't quite right, but we should test and see if our result's actually significant at whatever level that they pick. So in this case, they picked a significance level of a 0.1. This is a 10% significance level. This is pretty low. Usually we do a 5% significance level or even a 1% significance level, but a 10% significance level is a pretty low significance level. They still do it though, so it's not a bad problem. It's saying, is there evidence at the 10% significance level to suggest that the average lifespan of the bulbs differs from 10,000 hours? It doesn't say, is there evidence to suggest the lifespan of the bulbs is less than 10,000 hours? And it doesn't say greater than 10,000 hours. It just says differs from 10,000 hours. So could be higher, could be lower. This would be a two-tailed test. So when we go to write our hypothesis this time, because it just says differs, we're gonna have an H naught and an HA where our mean the first time is equal to 10,000. And the alternative hypothesis is that the mean is not equal to 10,000. Okay. So because that's just a not equal to sign, this makes it a two-tailed test. And so when I draw my picture, I'll show you what that means or what that changes about what we've been doing, because it does change something about what we've been doing. Okay. We're going to still go find our z-score the same way we found our z-scores all the other times. So our z is equal to the x bar minus the mu naught divided by our sigma over the square root of our sample size n. Our x bar was 9,850 hours. We're subtracting the 10,000 hours. Our sigma was 800. And square root of 64. So we should be getting a negative z for this one based on that numerator. So I got negative 1.5. That's going to let me go draw my picture now. So negative 1.5 is going to be over on this side. And we want a two-tailed test. So you're going to want stuff that's over here and over here. You want the right tail and you want the left tail if it's a two-tail test. This number, z is negative 1.5, that's going to give you this area. So what do we got to do to get all the area? Multiply by 2. Multiply by 2. So these should be symmetrical. So whatever that area is should be identical to whatever that area is. So when you go get this number from your z table, you're going to take that p-value and you're going to multiply it by 2 because you have another tail. That's what it means to have a two-tailed test. Okay, so I'm going to try and label this and say, this will come from the table. And then we also need this area. So we'll multiply by 2. So the p-value that I get from the table for negative 1.5 is 0.0668. So I got that p-value from the table. So I'm going to say 2 times 0.0668 is equal to 0.1336. So this is our p-value for both tails. All right. So what am I concluding? Am I rejecting the null hypothesis or am I not rejecting the null? So we're taking a look at our significance level, which was 0.10. And we got 0.13. So you could think of that one as a 0.10 and this one as a 0.13. This one's bigger. Darn it. So we don't get to say something interesting. Our p-value is bigger than our significance level. So we have to fail to reject the null hypothesis. Very good. Since our p-value 0.1336 is bigger than our alpha equals 0.10, we fail to reject the null hypothesis. Okay, so there is not sufficient evidence to conclude that the average lifespan for the light bulbs is, and what we're saying, our alternative hypothesis was that it was different than 10,000 hours. So we're going to say that we don't have sufficient evidence to conclude the average lifespan for the light bulbs is different than 10,000 hours. So you're always looking back at your alternative hypothesis to help you figure out what you're writing in that there is not sufficient, either there is sufficient evidence to conclude or there's not sufficient evidence to conclude. Then you basically state the alternative hypothesis right there. Okay, so what was different about this one was that when we were looking at the wording, it just said a different amount. It didn't say a higher amount or a lower amount. So that made it a two-tail test for us. When you write a hypothesis test and it's a two-tail test, your null hypothesis has the equal sign and the alternative hypothesis just has a not equal to sign. When you go to draw your picture, you're going to want the area in both tails, but the z value that you get is just going to give you the area in one of the tails. So you're going to have to multiply whatever you get by 2 for a two-tail test. So we did that here. 2 times the value that was in that one tail popped out our value for both tails. And you're comparing this value, the 0.1336, to your significance level. The alpha is 0.10. This one was bigger than the significance level though, so we had to fail to reject the null hypothesis. How you feeling? hypothesis testing is weird at first, but when you do a few in a row, then people kind of go, oh, okay, there's not really that much to do. It has weird vocabulary. So you have to get comfortable with what are all the symbols. The picture part's really important. I wouldn't skip the picture part. That's usually where people get messed up because they go, oh, I forgot that I was supposed to do 1 minus the thing. Like when you have the picture, it makes it more clear. If you don't draw the picture, it's really easy to get confused on what tail you want. So it's good to have a picture. And then I would say the most important part is remembering that your goal, like as a researcher, is to have something interesting to say. So you want to get to reject the null hypothesis. So you're hoping that p-value is small. But if the p-value is not small enough, we got to fail to reject the null hypothesis. I didn't plan more stuff for us today. I figured that you might be a little tired and I wouldn't go too crazy on stuff, but I'll stick around because I know some people had some like midterm type questions or whatever. So I'll still be here, but I'm gonna set you free. The sign-in sheet, if that could end up back on the front table, that'd be helpful. Otherwise, I'll see you guys next week.
So that's like the